Hello, welcome to my YouTube channel. In the first lesson of nuclear and particle physics, I talked about the relevance of studying nuclear and particle physics and explained the origin of nuclear and particle physics. Today we're going to have our second lesson, and I've titled it The Basics of Nuclear Physics. And in our lesson outline, we're going to talk about the nuclide notation, classification of nuclides, and units used in nuclear physics. Nuclide notation. We are going to start by explaining what a nuclide is. A nuclide is a specific type of atom characterized by its exact number of protons and neutrons in its nucleus. A nuclide is also known as nuclide species, and the symbol that is used to denote a nuclide is called nuclide notation. And as you can see, X there represents the chemical symbol of the element. Z is the atomic number, which represents the number of protons in the nucleus of each atom of the element, and A is the mass number, which is the sum of the number of protons and the neutrons in the nucleus of an atom of the element. N is the number of neutrons, and sometimes it can be represented including the number of neutrons as shown, and this other notation of a nuclide is particularly very important when discussing the classification of nuclides. Classification of nuclides. Nuclides can be isotopes, isobars, or isotones. Each category has something that is similar and something that is different. For isotopes, they have the same number of protons but different number of neutrons. For isobars, they have the same mass numbers but different number of protons and neutrons. While for isotones, they have the same number of neutrons but different number of protons. We know from our elementary knowledge in chemistry that a chemical element is defined by the number of protons in the nucleus of each atom of the element. So, if isotopes have the same number of protons, it simply means that when we are talking of isotopes, we are actually referring to atoms of the same element. But isobars and isotones are actually atoms of different elements because they have different number of protons. Let's look at some few examples. Let's starting with isotopes. One of the commonest elements is carbon, and carbon has three main isotopes. We have carbon-12, carbon-13, and carbon-14. Each isotope has 6 protons, but you can see the number of neutrons are different. The first one has 6, the second one has 7, the third one has 8, and this automatically makes them to have different mass numbers. Another common element is chlorine. We have 2 main isotopes of chlorine, chlorine-35 and chlorine-37. The atomic number of chlorine, or the number of protons in the nucleus of a chlorine atom, is 17, but they have different number of neutrons. You see the first one has 18, the second one has 20, and that makes them to have different mass number. An example of isobar is iron 58 and nickel 58. Both of them have the same mass number, which is 58, but you can see the number of protons and neutrons are different. Same with calcium 40 and argon 40. They have the same mass number, which is 40, but the atomic and number of neutrons are different. Now, isotones. Carbon-12, nitrogen-13, and oxygen-14 are isotones. Why? Because as you can see, they have different number of protons, of course, as expected, because they are atoms of different elements, but they have the same number of neutrons. Each of them have 6 neutrons. Same with boron-12 and carbon-13. They have the same number of neutrons, which is 7, but different number of protons. The boron has 5 and carbon has 6. So the question arises, what's the reason of classifying nuclide into isotopes, isobars, and isotones? Is it really necessary to know what isotopes are and the different isotopes that makes up an element? Yeah, it is very, very necessary in the study of nuclear and particle physics. When you know the different isotopes of an element, it helps in identifying atoms with unique properties, and you can apply them now in different ways. Let's take, for example, 2 isotopes of carbon, which is carbon-12 and carbon-14. Carbon-12 is very, very stable, and that is one of the reasons why it is used as a standard in determining the relative atomic mass of all other elements. Carbon-14 is radioactive. it is a radioisotope. That means it undergoes radioactivity, and it is used in different ways. And one of the ways is that it is used in determining the age of organic materials through a process called radiocarbon dating. Isobars are very relevant in understanding nuclide stability and radioactive decay processes. In beta decay, they are often transformed into each other. Let's take, for example, the beta decay of carbon-14 to form nitrogen emitting a beta particle. You can see clearly that carbon-14 and nitrogen-14 are isobars because they have the same mass numbers. What about isotones? The existence of isotones help us to understand that the stability of the nucleus can also be affected by the number of protons, even when the neutron counts are the same. So it helps us in identifying patterns and trends related to nuclear stability across different elements. So classifying nuclides into isotopes, isobars, and isotones is very, very necessary in the study of nuclear and particle physics. Units used in nuclear physics. Now, in nuclear physics, we're actually dealing with very tiny particles. Think of how small an atom is. Then what about a nucleus, which is about 100,000 times smaller than the atom itself? Let's consider the table below, which shows some known values of some quantities of carbon-14. You can clearly see that the value of the radius of carbon-14 nucleus in metre, the mass of an atom of carbon-14 in grams, and the energy released from the nucleus of carbon-14 when it undergoes beta decay in joules look very ugly and will surely make calculations difficult. The decimals are too tiny. So by changing to much more smaller units, like in the place of meter we use femtometre, and in the place of gram or kilogram we use atomic mass unit, which is usually abbreviated AMU or U for short, and in the place of joules we make use of electronvolt and its derivative, will actually help us to express quantities in nuclear physics in a more practical way, which will also make calculation easier. We are now going to see how the units we have just talked about are related to one another. Starting with femtometre, 1 femtometre is 10 to the minus 15 meters, or 1 meter is 10 to the 15 femtometre if we write it the other way. Atomic mass unit is defined as 1/12 of the mass of one atom of carbon-12 isotope. We know that the mass of 1 mole of carbon-12 is 12 grams, and the number of particles that contributes to this mass is the Avogadro's number, which is 6.02 times 10 to the 23 atoms. So if we divide 12 grams by the number of particles that add up to contribute to that mass, we'll know the mass of one atom of carbon-12. So if we take 1/12 of it, of course we have 1.66 times 10 to the minus 24 grams. We can express it in kilograms, and so we have this relationship between atomic mass unit and mass in gram or kilogram, which is 1 U equals to 1.66 times 10 to the minus 27 kilogram. So this can be used to change from atomic mass unit to kilogram, or from kilogram to atomic mass unit. Electronvolt is defined as energy required to accelerate an electron through a potential difference of 1 volt. And from my elementary knowledge in electrical energy, energy is equals to charge times potential difference. And we are dealing with an electron. And the charge on an electron is 1.6 times 10 to the minus 19 coulomb. So if we multiply it by 1 volt, we're going to have 1.6 times 10 to the minus 19 coulomb volt. And coulomb volt is joule. So 1 electron volt equals to 1.6 times 10 to the minus 19 joules is the relationship between electron volt and joules. And so we can use it to change from one unit to the other. And we can equally get derivatives of electron volts like kilo electron volt, mega electron volt, giga electron volt. So we are now going to see how we can express the quantities of carbon-14 that we talked about in terms of femtometre, atomic mass unit, and electron volt, or maybe one of its derivative. So finally, if we can express the quantities of carbon-14 that we talked about in terms of femtometre, atomic mass unit, and kilo electron volt, we have much easier values to handle. So it is much easier to handle 2.7 femtometre than to handle 2.7 times 10 to the minus 15 meters. And 14 atomic mass unit is easier than dealing with 2.32 times 10 to the minus 23 grams. So I'll leave it as an exercise for you to show how you can use the relationship that we have obtained between the corresponding unit to obtain this value of the quantities in nuclear physics. So we have come to the end of the second lesson. Our next lesson, we'll be dealing with some constant used in nuclear physics. The next upload is on Monday at 4 a.m. Eastern Standard Time. If this is your first time of visiting my channel, or if you have been here before and this video has been helpful to you, I would love that you like, share, subscribe, and click on the notification bell to be notified when the next video drops. Thank you very much. This is Physics with Omia.